Boy, okay, so this is like the third time I'm attempting to make the first slide of this video because people keep calling me and the phone keeps ringing, so let's hope we make it through this one. If not, I'm just going to talk right through the phone, so don't worry about that. So moving on to Chapter 8, a specific type of random variable distribution is the binomial distribution. I have a feeling some of you have seen binomial probabilities and binomial distributions before, but maybe you haven't. So we're only looking at 8.1 in the text, so don't get lost in geometric distributions. If you start floating into that part of the textbook, we don't cover it. So binomial distributions, again, the word binomial is talking about two outcomes. So we're only going to be looking at things that can be categorized into two outcomes, like making or missing a free throw, determining the sex of a child as male or female, or flipping a coin heads and tails. Oddly enough, other examples that can be looked at as binomial is drawing a heart out of a deck of cards. If you consider drawing a heart and not drawing a heart as the two outcomes, those would be binomial outcomes. You're going to be often asked about verifying the binomial setting, and the binomial setting has four main parts to it. So let me just drag them up here. So the first part is that each of the observations that you're looking at falls into one of two categories, success or failure. And again, you can manipulate that in a way that there can be actually more outcomes than you think, but you classify only one of those types of outcomes as successes and put the rest in the failure category, and you have yourself a binomial. The second piece is for binomial distributions. There are a fixed number of trials. So you have to be told ahead of time that you're only doing this 10 times or 20 times or 15 times. You can't have a countless number of outcomes. So this is going to be discrete. Geometric distributions, by the way, are the opposite. There can be infinitely many outcomes for geometric distributions. For those n observations, you need to know that all of the n observations are independent. This will allow us to use the independent rule or the multiplication rule for independent events when generating the probabilities. And then the last thing is about the probabilities, and specifically the probability of success. The probability of success in the binomial setting is called P, and it is constant for all n of the observations that you have in your setting. So those are the four things that make up a binomial setting, and we'll be checking through those as we go through examples and as you go through the examples in the book. So if the binomial setting is met, then we can talk about the random variable x again. So for the binomial setting, if we have a random variable x, we say that x is the binomial random variable. That's the binomial random variable. And we know that x is going to equal the number of successes. So the random variable x will take on values of 0, 1, 2, 3, 4, 5, and then depending on n, up to n successes in that setting. Notice I did say 0 because you could have no successes. And shorthand, similar to normal notation, if we do a capital B and then n comma p, these are the important characteristics about the binomial setting, that something is binomial with n observations and a probability of success p. With this, we have to talk about the binomial coefficient. So the binomial coefficient tells us the number of ways to arrange k successes from our n observations. So I'm going to pause and write that down. I will be right back. All right, so there it is. And as you read that, you may have a word that comes to mind in your head that you've seen before. We are going to be talking about the binomial coefficient as determining the number of combinations that we have. So we are going to be dealing with combinations, not permutations. And again, if you had a horrible experience with this in the past, don't worry about it. Not super bad in the statistics setting. Some new notation for you, or possibly old, I don't know. We talk about this notation, which is read n choose k. There's no fraction bar or anything, but the n is above the k. And this is the formula that determines the number of combinations you can have with n observations for k successes. And it's n factorial divided by n minus k factorial times k factorial. Where again, factorial just means that string of multiplication starting at n going all the way down to 1. So n choose k. This tells you the number of ways in which we can look at the arrangements of k successes from n observations. By the way, so that you know, n is always greater than or equal to k. The most number of successes you can have for k would be the n observations, and generally it'll be less than that. So we're going to be working with this a little bit today as well. Alright, so let's talk about actually calculating a probability for the binomial random variable. So in this statement, there's a little mistake here. I just have to point it out that it's missing the 0 up here. So this should be 0, 1, 2, 3, 4 up into n. If we want to generate the probability of x equaling k, the probability that the random variable takes on a certain number of successes, we would look at n choose k, the binomial coefficient, the number of ways of getting these different arrangements, times the probability of success raised to the k power. So we have k successes, and then we have failure, 1 minus p, to the remaining number, n minus k. So if you want to look at it, this is the pk. P to the k is the probability of success raised to the number of successes. So if k was 3, you would have p to the third, because you have three successes, and they're independent, so we can multiply them. And this over here, the 1 minus p, is your probability of failure to the remaining number of observations minus successes. So again, if you had 10 observations and 3 successes, that would mean you would have 7 failures. The n choose k part, that n factorial over n minus k factorial times k factorial, tells you the number of different combinations you can have of this happening. So if you have 3 successes out of 10 trials, remember that those 3 can be arranged in any way. The first 3 could be successes and the last 7 could be failures. The first 7 could be failures, the last 3 could be successes. N choose k is going to tell us how many of those combinations we have to worry about, and then the probability of having that happen. So let's go through this example. Take a look at example number 1. Emily shoots free throws at a known rate of 48%. What is the probability of Emily making 4 out of 10 shots? So first question is it binomial? So she's taking and making a shot or missing a shot. So yes, we have success failure. There are a certain number of observations that are set. There are only 10 shots that she's taking, so we know that in this particular case n is equal to 10. The probability of success doesn't change for those shots, so p of success is 0.48. And those shots should be independent, or at least we have to assume them to be in this particular setting to be able to do the problem. We want to know where x is equal to k, where the random variable x is taking on 4, and this is our k and our n choose k. All right, so this is what we want to find. And to find it, we're going to write a probability statement. We want to find the probability that x is equal to 4. It's the probability she makes, and we're only talking about exactly 4 out of the 10. We don't care the order in which she makes them. We just care that she makes 4 of them. So that would be n choose k, so 10 choose 4, times the probability of success, 0.48, to the 4th, because we have 4 successes, and then the probability of failing, 0.52, to the remaining n minus k, or 6 ways of failing. To do this out, we have to look at the binomial coefficient here of 10 factorial over 6 factorial times 4 factorial. There's the number of combinations, and then we're just going to throw this in our calculator in a second anyway. We'll keep these decimals to where they are. In terms of 10 factorial over 6 factorial times 4 factorial, you can do it out. Maybe you remember on your calculator how to do it. If not, it would be a great day to search how to do factorials on your calculator. That 10 factorial divided by 6 factorial times 4 factorial ends up being 210. There are 210 different ways to arrange these outcomes of successes and failures, times 0.48 to the 4th, times 0.52 to the 6th. And dumping that all in your calculator you should find that the probability of x equaling 4 is 0.2204. And that is the probability of Emily making exactly 4 of 10 free throws, given she's a 48% free throw shooter, with shots being independent of each other. All right, let's talk about a quick way to get that 10 choose 4 too. Also, not 2, also. All right, so many of you may remember that there is a way to do combinations on your calculator. If you use the math and then go over to probability and down to option number 3, that is the way to do combinations. So if you want to calculate the binomial random variables coefficient, the binomial coefficient for a binomial random variable, if you want to do 10 choose 4, you choose option number 3 out of the probability menu and you put in your 10 observations, 4 successes, and it's going to spit out the 210 for you. So don't feel that you need to do the factorial all the time, but understand that that's where it comes from. The other thing is that your calculator can obviously go through the commands and do the calculations for you. So for any probability where x equals k, where x is a binomial random variable, there is an option in second vars that is called Binome Pdf. Now, Binome Pdf is option A in the second vars menu. And what this does is it calculates an exact probability for x equaling k. So it's a PDF, it's a particular value for the density function versus a cumulative value. So I know we said we never use normal PDF. In this case, Binome Pdf and then Binome CDF are going to both be used. For a specific x equals equation, we're going to be using the PDF version of Binome. The entries for this are your n observations, your probability of success p, and then your k successes. So if you want to try it out, you can go ahead and do this, and Binome Pdf should give you the 0.2204 value that we got on the previous page. All right.